Okay, thanks everyone. Welcome to the CAD for Assurance webinar. And I believe this is the 8th or 7th in the
The
series. And each
seventh.
7th in the series. Thanks here for correcting me. So of course, there are more to come. And each of these webinars, the tool demo webinars, has featured two different tool demos or demos on benchmarks. In addition, as you know, we have also having panels as part of the CAD for Assurance initiative. I just want to give you a very quick overview of the CAD for Assurance initiative, which is started October 2020, and it was done by the hardware security community. There are large number of members who came forward and wanted to create a platform for academic dissemination of open source EDA tools, benchmarks, and metrics, which are targeted to assured systems and hardware. So they are all targeting hardware assurance and system assurance. Right now, we are very glad to see 55 different CAD tools which are posted in the website from more than 70 different contributors. So that's definitely really encouraging to see the community came forward and wanted to share their CAD tools for assurance. And also in a little bit more than a year, we have got over 6,000 unique users of the website. As you can see from the diagram below, this is taken from the Google Analytics page for this website. It's very encouraging to see large number of users coming to this website and visiting using the tools. And we have, of course, more than 22,000 page views. That's again very encouraging. We'll strongly encourage you to contribute if you have an EDA tool or benchmark or any data or even publications relevant to assurance. If you would like to share with the broader community, we'll strongly encourage you to do that. The website has a tab where you can upload your contributions. If you have any question, definitely you can get back to myself, Dr. Gang Q, Dr. Shungi Ho, and Dr. Jin. All of us are joint organizers for this webinar series. And we are also pleased to have a number of co-sponsors for these events. IEEE CEDA, a Hardware Security Technical Committee, which is part of IEEE CEDA, Mercury, HII, Northrop Grumman. They are also co-sponsor for these events. And again, I would like to acknowledge their sponsorship one more time. Really grateful for that. And if you are interested to see what events have been organized through this initiative last 1 year, particularly 2021 has been very active. We had number of events, pretty much every month we had events. And if you want to look at the calendar of events and see the video recording of those events, in case you have missed them, you can go to IEEE CEDA website or the CAD for Assurance website. You will have a lot of information on that. And just want to let you know that the recent panel, that's panel number 3, which was organized in October 2021, the recording is available. It was a very successful, very well attended panel, like the other two panels, panel 1 and panel 2, and the recording for most of them are available. I believe panel 1 is not fully available, not the entire recording, but you'll be able to get at least good amount of information by visiting CAD for Assurance website and IEEE CEDA website. There are 2 other panels upcoming, panel 4 and panel 5. They are focusing on very important topics. If you're interested, you can register ahead of time. Registrations are required for all these events and they are free. And you can do that by visiting the IEEE CEDA website. With that, thanks again for attending. I would hand over to the first presenter for today's webinar. And that would be Prabuddha Chakraborty, and Dr. Jin would briefly introduce the presenter.
Thanks, Dhruv. So as Dhruv mentioned, this is the second year for the CAD Assurance webinars. This is our 7th tool demo, and today we have 2, and the tradition that we always have 2 tool demos in each webinar. And today we have 2 of them. One is from Prabuddha Chakraborty. He's from University of Florida. His tool is SAIL, Machine Learning Attack on Logic Locking and Obfuscation. Then we will have another tool, Plan Power SideChannel Evaluation from Lakshmy and Chester, IIT Madras. So without any further delay, Prabuddha, can you share your screen and start the introduction?
Thank you, Professor Jim. Yeah, we'll get started. So can you see my screen?
Not yet.
Yes, yes, we can see now.
Oh, now I can see it. Yes.
Yes,
Okay.
yes.
Fantastic. Okay, so let me get started. So I'll be presenting SAIL. I'm Prabuddha Chakraborty, and my co-authors are here as well. And I'll briefly go over the basic idea of SAIL and how we got motivated to do this work and what it means from a theoretical standpoint. And then I'll go over to our implementation of SAIL and explain how the tool works and how one can use this tool for their research as well. So as you know, the current semiconductor supply chain has many entities involved. It's a horizontal supply chain, right? And unfortunately, these entities do not trust each other. And a rogue employee or some malicious entity itself, if the whole entity is malicious, they can lead to modification, they can lead to reverse engineering of the IP or the IC involved. And this can eventually lead to overproduction, reselling, and remarketing. So that's a huge problem that we're dealing with. And one solution to this, some of these problems, is logic locking. What happens is that you have this design and you essentially insert a few key gates in the design. And what happens is that unless you enter the right key, the design will not function normally. So this ensures functional security. And generally, we do our resynthesis of the design after inserting the key. And that way, we try to attempt to introduce some structural changes in the design. And that way, we are trying to prevent reverse engineering of the design. That's the tradition. And there have been, over the years, many attacks or evaluation frameworks that tries to ensure security of the logic locking that has been done from a functional standpoint, such as the SAT attack or the AppSet attack or the SMT attack that has been proposed. These attacks tries to ensure security from a functional standpoint. But what about the structure and the structural security? What about reverse engineering attacks that can be carried out? And can these reverse engineering attacks or structural attacks lead to more powerful functional attacks? That's what we wanted to understand and analyze. To do that, what we did was we took some designs and we inserted key gates in the design, and we essentially took the design and synthesized it, and we saw the kind of changes that were introduced due to the insertion of this key gates. And what we saw is that these changes from pre-synthesis to post-synthesis localities in the netlist were sporadic. These changes were small and distributed and very small in terms of the number of gates being involved in the changes. And there was a huge bias in the kind of rules that were being used by the synthesis tool to carry out such changes. And that led us to believe that, hey, if the rules are deterministic, and if the changes are small, then maybe we can learn these changes that are being introduced, learn the rules, and then reverse these changes. And that would enable us to carry out a structural attack or reverse engineering attack on the IP. So that motivated us, and we went ahead, and what we did was we essentially took post-synthesis the designs and the pre-synthesis design pairs, and we trained the AI model to learn the transformations and to capture this transformation bias. And then given the design and the evaluation, we could structurally unlock the design, and we could also quantify the structural defense of such a locking technique. Now, how do we get the training set? That is probably the most interesting part here. So let us go deeper into that portion first. So what we did was, what really happens in a logic locking scenario is that you have this defender, and the defender is trying to insert key gates in the design. And then once the key gates are inserted, the defender synthesizes the design, and these key gates in blue transform into something else. or the region around which the key gates are inserted transform into something else. And that you see from this transition from blue to red. And this design, the synthesized lock design, is what is essentially given to the attacker. And what the attacker will do is, or rather say what we are doing is, we take this lock design, we insert more key gates into it. And then we carry out the synthesis on top of that. And now we have these green localities because we know where they are because we inserted them as from an attacker standpoint. And we know what kind of transformation happened in those localities. That is the orange, that is the yellow locality. And we have a one-to-one mapping between these two. And that's how we get the training data set. And learning from that, we try to convert the red localities back to the blue localities. So coming back to the flow, we got the training data set directly from the design and evaluation because we took the design and evaluation and we inserted more key gates into it and tried to learn the changes that are happening through synthesis. So this process we call the pseudo self-referencing. It's kind of self-referencing, but we call it pseudo because the design already has a few log gates in it, so it's not a clean self-referencing, which is still good. And that's the reason we do that. That makes our analysis golden free analysis because we do not assume that we have the actual IP without any locking gates in it. And it also makes our analysis Oracle-less. And we had tremendous success. We were able to unlock different logic locking techniques with great accuracy, with very good R metric. R metric is a metric that we propose to kind of capture the structural recovery that we are getting. And it also kind of measures the structural recovery efficiency of this stack. And we were able to get really good accuracy in our metric and pretty much broke the standard logic looking schemes from a structural standpoint. And we also got really good accuracy for large expression spaces because as you try to predict a bigger subgraph, your expression space kind of blows up to the order of to the 16, which is really high. But we still were able to get really high accuracy given such a high expression space. So on top of that, when we wrote our journal, we also introduced a metric called the SIVA metric, which is kind of a theoretical upper bound of cell. And this is a theoretical metric that we have proved to be the upper bound, and you can compute it directly on the lock design. You do not need to do any training. You do not need to apply the full cell flow. So this will also help you to do a quick evaluation before running cell, if that's the goal. And we have also leveraged cell to carry out other attacks called a surf attack. In surf attack, what we do is we just take the design, we run cell on it, and then we get the exposed localities, and then we use a surf analysis to kind of refine the keys and through some optimization techniques, and we get the actual key back. And we had great success there as well. We were able to recover 100% of the key in some of the caches. And very interestingly, we were able to unlock 6288, which is traditionally a SAT hard design, which is SAT attack cannot break 6288 because of it's a multiply, right? So, but through structural analysis and subsequent optimization technique through SERP, we were able to break the even C6288 as well. And that's what we did. And after that, the community has taken over, and they have done many different works around sales, snapshots, sweep attacks were introduced. OMLA was introduced. I think that was from NYU versus Goose Group. And Uncell was there done as well, trying to defend against Cell. And Cell also has inspired a series of series of Cell hard obfuscation schemes such as Leguanzaro. And so what, at the end of the day, what Cell gives us? Cell gives it's a new type of attack. It's a structural attack, and it can exploit traditional logic locking techniques. And it is beyond that, beyond being an attack, it's an analysis platform. You can use Cell to identify and localize the structural vulnerabilities in the IP. You can also quantify the goodness of the structural obfuscation that has been carried out. So at this point, Cell should be ideal for verifying the structural security of the design. And this is kind of a counterpart of what SAT does, because SAT ensures functional security, and Cell is the structural counterpart of SAT, you can call it that, where we kind of quantify how good the structural defense is. So together with SAT, Cell can lead to a more comprehensive logic looking analysis. And we believe it can be also extended to sequential obfuscation as well. And this paper is generally highly received. It got a bunch of awards, and the cell tool is available. You just have to request us, and we'll add you to the repository for the tool. So let us now go back to the main focus of this talk, which is the tool, right? So what happens in this tool? So you start up with this Netlist 1. So that's the defender. This is kind of going back to what I already said. So you have this Netlist 1, which is the original netlist without any locking, and then you insert your key gates. That's what the defender does. And then the defender also does a synthesis to kind of hide the key gates, rather, to kind of meld it with the design, so to speak. And this is where the attacker takes over. The attacker takes this netlist 3 and starts the attack. And what the attacker do is the attacker inserts more key gate into it. So this is, we call it relocking. And then the attacker carries out one more round of synthesis, the resynthesis step, and gets netlist 5. Now, the attacker looks at netlist 5 and netlist 4 and generates those, extracts those localities, pairs, before and after synthesis. Because the attacker has done the locking themselves, and the attacker has also synthesized the design. So the attacker knows exactly which locality changed into what locality after the synthesis. So that way, the attacker forms these pre and post synthesis pairs. And as you can see on the left-hand side below, these pairs, post and pre-synthesis pairs, and trains the model. And then the attacker tries to reverse the changes that were introduced from netlist 2 to netlist 3 using the model that is already trained, right? Because the attacker doesn't have access to netlist 2. Attacker has access to netlist 3. So from 3, the attacker takes it back to 2 using the model trained. So this is the reversion phase. So we'll look into both of these stages, how the cell handles the training and how cell handles the reversion. We have 2 different scripts to do this task, and I'll show you how to run them. And remember, everything is happening in this locality level, and which is essentially locality. I'll refer to this as locality. What is a locality? Locality is nothing but a subgraph in the netlist. Okay, so let's move forward. And I'll come back to this slide again. Now I have to make this a little interactive because I'll be going back from the slide to my terminal to show you how the tool is working. And so this slide essentially has some of the inputs to the tool explained. So I'll come back to this. So what I'll do is I'll stop sharing my screen, and I will actually share my whole screen so that I can have a more interactive session. So can you see my whole screen or no? Anyone?
Yes, we can see. I think we can see the whole screen. Yes.
Do you see my terminal?
Yes.
Okay, perfect. Okay, now we are ready for the.
But maybe you need to make it a bit larger. Okay. Yeah.
Yeah, I'll do that. I'll do that. Sure. Okay, so the tool is available in GitHub, so you'll get access to it in this format. It's a repository. I'll add you to it when you make a request, and it essentially has a binary and all the dependencies of the binary there as well. So you do not really have to install anything. You just, extract and run. So that's the best thing, right? So there are some requirements which I'll go over. So what you do is you clone it, and this is something you'll get this binary.zip. You unzip it, and then you first navigate to your binary, and these are all the libraries that are there already in SO format for you to use directly. And let me quickly go over the inputs of the tool. So first we want to do the training, right? And then we would like to do the evaluation. So here we provide you with a few sample training and testing netlist, but of course you will be using your own. But for now, so let us look at the test first, because this is where the obfuscation started, right? So this 10 C1355 pre is the pre-synthesis but locked design. And this is from the defender perspective. So the defender generates this design. The defender inserts some key gates in the design, and you have to insert it in as a register. That's kind of important, and keep a note of this name. So here the name is key in, because we'll be needing that. And this is the first lock design. You take the clean IP, you put a gets in it, put some gets in it, right? And then you synthesize this pre and you get the post version of the same thing. You still have the key gates and everything, but of course the kind of circuit kind of changes once you do the synthesis, right? So this is the pre and the post designs, and the goal of the attack is to, given the post design, can I take it back to the pre design, right? So now the attacker takes this post design and the attacker will carry out the pseudo self-referencing. That is, the attacker will insert more key gates into it, which I will show you how that has happened. So we do that, we open it. So this is the pre-version from the attacker's perspective, pre-synthesis version. So the attacker has inserted more key gates, and as you can see, the key in register, this was, I hope you can see, the key in is the original key gates that were inserted. And the key in pseudo is the new key gates that were inserted by the attacker. And then the attacker carries out one more round of synthesis, that's the standard that we're doing. And the key in pseudo is still there. So the attacker kind of knows the locality around key in pseudo and how they have changed, because the attacker has access to both the pre and the post synthesis, whereas the key in pseudo is concerned, right? So these two designs where the key in pseudo is present will be our training set, and then we'll try to attack the original design from which we started. So let us look at the two. So how you do the training. So this is the command for training. All you do is you just simply go to the binary and you just paste this command. So I'll just go the command first. So it's called train model, LRD train model, and you need to provide X node cut. And this is essentially the locality size of the input locality size, which is the input meaning the post synthesis locality. So I'll go over this one more time with you in the slides, but let me quickly explain. And then this in-depth cutoff and X in-depth cutoff and X out-depth cutoff is essentially the cutoff for the breadth first search that we do to construct the locality. And the Y node cut is the number of gates in the predicted locality. And the Y depth cutoff is again the breadth first search that we do to construct this locality. And the max key bit is the number of key bits in the biggest design that you have lost, pretty much. So it doesn't really matter as long as it is greater than the key bits that are present in the training data set, any training data set. And then you provide the key base name train. This is essentially the name of the register that is being used for inserting, for relocking the design. So if you remember, we had this key in pseudo register. So this is essentially the key in pseudo that has been inserted by the attacker. So if you specify the name of that, that's all. Okay. And then this is essentially the path to where the dataset is present. So this will be the path to this the train dataset. And leave is -1. So leave is where we will add support to other libraries. Right now, we only support GSC. In future, we'll support Skywater and other things. So this will be used later. Right now, this is dummy. Just keep it -1. It's not going to be a problem. And then Verbose will allow you to see more details if you want, and regarding the tool. But just keep it 0 if you don't want to see all the messages. And then the model out path is essentially where you would dump the trained model, right? So now let us look at the X node cut and X in depth cutoff, just to make sure you completely understand that. I'm sure you do. But so this was the pre-synthesis locality and the post-synthesis locality. So the X node cut is the number of gates in the post-synthesis locality. So what is the post-synthesis locality? This is the locality you are looking at to make your decision. And the pre-synthesis locality is the locality that you are trying to predict. So X node cut is associated with post-synthesis, and the Y node cut is associated with the pre-synthesis. It's the number of gates in this locality, essentially. And the depths are essentially controlling the breadth first search for generating this locality. So going back, now we're going to run this thing. So we're going to take this script and we will just go to the binary and you just put it there and you run it. It should work. And it said learning is done. And you can just simply go out and you'll see this model here, RNSOR sample model.npy. This is the model that you trained. And now let's use that model. So how you use it? You go to the binary folder, and there is a script called celr_devaluate, and you again have to put in the x0 cut and the x0 in depth, the depth cutoff, and you also have to provide the y0 cut and the depth cutoff and the maximum key. This is exactly the same that you use for training. And then you also have to provide the key base name for test. Now remember, for testing, what are you testing on? So let's go back. So you are testing on these test data sets. This is before you did the relocking and all that, right? So this is the original two benchmarks. So let me close all this. So this was the original benchmark. This is before synthesis and the post is after synthesis. So here the key gates are, the key inputs are called key in. So you need to specify that. And note that there's no key in pseudo here because this is before we did the relocking stuff, right? So you provide that here. You say, okay, evaluate, okay. So you say, okay, my x0 cuts and y0 cuts are all this stuff. This is exactly the same as before. And then you provide the, there you go, the key base name test. The key base name test is key in. And then you also have to provide the pre-netlist, the pre-synthesis netlist. And you also provide the post-synthesis netlist, which is just give a path to that pretty much. And the pre-synthesis netlist is actually not used to run the attack. It is something the attacker doesn't have access to. The attacker only has access to the post-synthesis netlist. But based on that, the attacker will predict some of the components, some of the subgraphs in the pre-synthesis netlist, right? And just to get an accuracy as to how good that attack was or how successful that attack was, that's why we need the pre-synthesis netlist. That's the only reason we provide it to the tool, so that we can get an automatic report on the accuracy. Otherwise, the pre-synthesis netlist is assumed to not be available to that attacker. And then you also provide the model that you used to use, and you provide a temporary folder where all the logs and stuff will be stored. And the top in indicates, this is again used for computing the accuracy. This is essentially saying that consider the top 5 candidates that have been predicted. And if the correct one is within the top 5, we call it a correct prediction. That's essentially what it means. This is just for computing the accuracy. It's just not much to do with the actual prediction itself. So now I'm going to run the evaluate quickly. So again, you go to the binary and you will be running this evaluate. And you'll do the evaluation and it'll report you the accuracy. So it is 50%. That's the accuracy. You get an R metric value, and you also tells you that the 4 out of the 8 were correct and all that. Now, how do we improve this accuracy? So this is a little low, right? It's 50%. So a few things you can definitely do. First thing you can do is you can say, okay, I am going to evaluate with a better model. And we provide you with this model that is already in the package. We call this the random SOR foam model, which is actually trained with a lot of random SOR obfuscation netlists. So it has a bigger library, so to speak, or a knowledge base. So the attack will be much better. And you can provide a link to that model and you run the same evaluation and you'll get a little better accuracy. You have now 62%. Okay, great. Now, can we do more than that? Now, this is where things get interesting. What we allow in Cell is to support ensembling. That is, we, instead of looking at, if you remember here, instead of looking at the post-synthesis locality with only 3-gate post-synthesis locality, we can look at bigger subgraphs in the netlist to make our prediction. So that is why it gets tricky. And we can say we'll look at 3-gate localities. We'll also look at 4-gate localities. We'll also look at 5-gate localities. We'll also look at more bigger gate localities to make our prediction. And if we allow such a flexibility, and that way, if we create an ensemble through that mean, then the prediction accuracy generally increases, as we show in the paper. And what all you have to do is just say, hey, look at 3-gate localities, put underscore there for X input. Also look at 4-gate localities, also look at 5-gate localities, and then make your prediction, please. And then you run the model, you give all the paths, you give other parameters remains the same. And then you run it, and you get 87% accuracy. That's great. Now, all out of the 8 that have been provided, 7 are correct. Now let us go a little deeper and see how what it looks in the logs and what kind of logs are generated and how you can make better use of the log itself. So the logs are in this called temp file. So you go to temp and you see the CLRD results file. There are other things that have been dumped here, but I think the most important thing is the results, because that's the more human readable format. And what it essentially tells you that the key bit 5 was X was, this was the graph, how that just is the matrix of the graph, essentially matrix of the graph. And these were the gates, XOR gate, another XOR gate, followed by a XOR gate. And this was how they were organized. This was the input that were provided. This is the post-synthesis locality that was provided to the tool, to the analysis. And this is what the analysis predicted. Analysis predicted that, wait, looks like the middle XOR was actually an inverter in the pre-synthesis state. And this was how the graph was organized. This was how these gates were structured. And in reality, it was so. So this is a correct prediction. So this actual part here. And then again, for another key bit, you can do the same thing. So not only are we reporting the accuracy and the R metric, which you can of course use for your paper, you can also look at the prediction that we are making and potentially carry out a second stage of attack, carry out a more pre-prediction attack, or carry out one more round of structural attack on top of this. So that way you can expand. And this is exactly what we kind of did for surf attack. We looked at these predictions and we tried to predict the key, right? That was the entire surf attack that we did off sale. So that's something you can get from here. And of course, you will be getting the accuracy and the R metric directly from the terminal, which you can report. And you'll also get some interesting here. This is the error dictionary. So what this means is that the first number in this dictionary, I hope you can see this. This is rather small. So what I'll do is I'll copy this and put it in my text file, and that way I'll show it to you better. So this is what was predicted. And this error dictionary essentially means is that you have the link error underscore the gate error. So 00 means that when I did my prediction, seven of my prediction had no link error and no gate error. And one of my prediction had no link error, but 2 gate errors. So this is what essentially this dictionary means. And as you run bigger designs, this will be more populated and it will have more entries in there. So this is something you can also report. And how we generally do it in our paper, when we reported the accuracy for cell, what we did was we essentially ran it for different designs, and we reported the accuracy in the R metric, and we varied the top metric that we use, top 1 through 5 and 10, to kind of get how the accuracy kind of increases as we allow more candidates to be considered. And you can also vary the LX. LX essentially is the X node cut, because if you have more, if you allow more information to be available for the prediction, then of course the accuracy increases, generally speaking. And this is what we also see in our paper. As we increase the information in the ensemble, we have generally better accuracy. So that can also be reported. So with that, I'll stop. I think I'm on time and I'll be able to take any questions. I know I have covered a lot of technical details, and I think it will be better if we go to the Q&A. That way I can answer your questions better.
Thanks, Prabuddha. So it seems that your advisor had already answered some questions while you are presenting.
Oh, thank you. Thank you.
Sure, there are quite a few questions, I think 4 at least I saw. So some of them I tried to answer, but we'll open it up to the audience and see if there are other questions.
Yes. Thank you, actually, when I share my screen, I cannot see the questions, so thank you.
Yeah, so there were 4, and all of them have been answered. So let's see if the audience have more questions.
And if you do, you can put it in the Q&A section of that.
Right. So let me take a look at the questions and see something interesting. Does the choice of synthesis tool matters? Yes, it doesn't matter. And we have actually tried other synthesis tools as well, and Cell performs really well on those as well.
Yeah, so Prabhu, the one point I would like to highlight here, because I think that's the essence of several questions, is that what if we do not have the right training set, or if the attacker can exploit the fact that there are so many possible synthesis tools? How do you learn the rule of transformations reliably? So interestingly, that's definitely a very powerful question. So what happens is that if you think about logic synthesis, which is implemented by pretty much all synthesis tools out there today, there are finite set of rules which we apply today to optimize a design for area of power performance. And these rules are kind of textbook rules. And there are, we did count, there are few hundred possible rules possible. In the paper, we talk about those rules.
Right.
And for a good machine learning tool, it's very easy to learn those rules. As long as they are very predictable for a given Boolean logic, the number of possible transformations a logic synthesis tool would explore is finite and very limited. So it's quite possible for machine learning tool to learn those and then reverse engineer so that we can get back to the original structures. And that's exactly what we have seen repeatedly. And
to add to that, what we did was, for the experiment, we trained on the transformation observed through synopsis, and then we essentially generated another test data set using cadence, and we did a cross analysis, and the accuracy drop was very little. So it means that essentially both of these synthesis tools were using the same kind of rules for transformations. And these results are there in the SideChannel paper. Right.
There's one more question in the Q&A window.
Yeah, so Chris Clark did submit a question right now, and I think this is a very, very good question. So the question is that the key aspect of this approach is for the attacker to add additional locking structures. It seems like this assumes that the attacker knows the locking scheme used in the original design and or has access to the same locking tool. Is this correct? The answer is yes. The assumption for any security technique which we are looking at is that the security algorithms or the transformation algorithms should be public. So we assume in our attack, and pretty much every attack which are out there, is that it follows this Kirchhoff's rule, where we assume that the attacker does not know the secret, which is the logic locking or obfuscation key, but knows the algorithm. So yes, we assume that the algorithm is known. Even if we do not know the algorithm, if you know in general how logic locking works, if there are let's say minute nuances which, let's say, the attacker does not know, but if the attacker knows that, hey, there is a key gate inside it, and then there's some transformation happening around the key gate, then it's still possible to apply cell technique to reverse engineer the original design. But for our study, we have assumed that we know the algorithm.
And yes, to that point, we actually also have results in the journal paper saying that what happens if we do not know the logic locking scheme, and in worst case, what if we do not know both the logic locking scheme and we also do not know what kind of synthesis tool has been used? And we have presented those results as well, and the accuracy is generally high as well in those cases. So even if you do not have access to the exact logic locking scheme that has been used, you can still do a significant amount of recovery using cell if you train on other techniques that is more well known.
Okay. Okay, I see Sarup is also typing the answer. So I would like to thank Prabuddha again. And if you have any questions, definitely search on our CAD for Assurance website for the tools, and then you can contact the author if you have more questions. And I just want to repeat again, this is a tool demo. That's why our presentation is short. The majority of the time it used to live demo our tools. Okay.
Thank you, Professor Jim. Thank you.
Thanks. Now let's move to our second presentation. So Chester or Lakshmi, any of you will share your screen?
Yeah.
Yes.
Yeah.
I'll just share my screen.
Yes.
Is the screen visible?
Yes. Please go ahead.
Yeah. So hello everyone. Today I am Lakshmi and my guide is Professor Chester Rebeiro from IIT Madras, India. And today we will be presenting our power side channel analysis using two tools, Plan and Fortify. The brief outline of this talk is as follows. We'll start with an introduction to power side channel attacks and the power side channel vulnerability estimation techniques. Then we will discuss the two tools, Plan and Fortify, by giving an overview of each tool, the main steps involved. We'll have a hands-on demo of both the tools and how to run them. And we'll briefly discuss the results and limitations of both the tools. Finally, we'll discuss the references related to the tool usage and licensing and all the repo and documentation links and so on. So let me start with a brief introduction to power side channel attacks. These attacks essentially exploit the fact that the instantaneous power consumption patterns of an electronic device may indirectly reveal the data being processed or the operations being performed by the device. Power side channel attacks have a wide variety of use cases, such as stealing secret keys and passwords, reverse engineering software, as well as machine learning and deep learning algorithms, recording the key presses of users, monitoring web browsing activity, and so on. There have been numerous works which have practically demonstrated these attacks. So it is very important that electronic devices are properly protected against such attacks. In order to do that, we should be able to estimate the power side channel vulnerability of an electronic device. Conventionally, this has been done using post-silicon techniques, which analyze an already manufactured electronic device for vulnerabilities and check whether it meets the required security standards or not. Post-silicon techniques provide an accurate estimate of the power side channel vulnerability of the electronic devices. However, if the device is found not to meet the required security standards, then there is no option but to discard the device and refabricate it by applying the required countermeasures, which makes these techniques too late in the design cycle to take any corrective measures. More recently, pre-silicon techniques are gaining more popularity. Pre-silicon techniques analyze the design itself for potential vulnerabilities. These provide an early and fine-grained estimate of the side channel leakage. However, these techniques may be less accurate than the post-silicon techniques, and also they might require a large number of simulations and statistical analysis. We will touch upon this in more detail in the coming slides. In today's talk, we will be looking at two recent pre-silicon side channel vulnerability estimation tools, namely Plan and Fortify. As I mentioned before, the main aim of these tools is to provide a quick and fine-grained estimate of the power side channel vulnerability of a pre-silicon digital circuit design at the RTL or gate level netlist stage. To understand the key idea of how these tools work, let us consider an example of a simple circuit where we have highlighted two signals. SIG denotes any typical signal in the circuit, whereas oracle or the reference signal denotes a secret carrying signal in this circuit. So in this case, we can see that the signal P is the output of the XOR operation between some input and a secret key K. So P is considered to be the oracle or reference signal, which carries some secret information in this circuit. Now, the key idea here is that the power consumed by a signal depends on its toggling behavior. That is the transition between a 0 to 1 or 1 to 0 bit. So essentially, the power consumed by a signal depends on the data that it carries. Also, the power side channel leakage essentially denotes how much information about the secret, like the oracle signal, is carried, can be inferred from the any other signal SIG in the circuit. So in other words, we can say that the correlation between the data of the signal and the data of the oracle signal gives us an estimate of its side channel leakage. Plan quantifies this correlation by using statistical techniques, whereas Fortify adopts an analytical approach to quantify this correlation. In the coming slides, we will look in more detail at both Plan and Fortify. Let me start with Plan, which stands for Power Attack Leakage Analyzer. Plan takes as input a digital circuit design at the RTL or gate level netlist stage, along with an oracle or reference signal in the design. First, Plan performs a large number of behavioral simulations and collects the traces of all the signals in the design, including the oracle signal. Then it performs pattern extraction, wherein it computes the pairwise Hamming distance vectors between the different values taken by the oracle as well as each signal in the design. Finally, Plan performs correlation analysis by applying a metric known as the side channel vulnerability factor, which is based on the Pearson's correlation coefficient, in order to compute the correlation between the above computed distance vectors, thereby giving the signal-wise side channel leakage scores. Now let me give a quick demo of the Plan tool. So here we have the GitHub repo where we have both the tools, and there are a few steps to set up this repo after cloning it. Having done the setup, we can jump directly to the Plan tool, where we have provided a README file with all the required details. The Plan tool has been implemented in the form of a Python file, and it also includes a few bash scripts which are invoked internally, which perform all these steps which we have described in the presentation. In order to run the Plan tool, we can just run this Python script run plan.py with a few input parameters, such as the details of the input Verilog file to be analyzed, details related to the secret key, simulation script, which is used in the behavioral simulation step of Plan, and so on. So let us take an example of a 2-bit full adder design, which can be analyzed using Plan. So for this, yeah, so here is the full adder design, which we'll be using as the input to the Plan tool in our demo. This design essentially captures this kind of a circuit where we have a secret key and an input A, which are first carried out an XOR operation in order to obtain the ENC-A signal, which acts as the oracle in our case. This, along with two more inputs, B and C, are taken as inputs to a full ladder circuit, which provides the sum and carry output as the output signals. And in order to simulate the circuit, we make use of this bash script known as fa2simulate.sh. This script basically plugs in different random values for the inputs A, B, and C into that Verilog file and performs the simulations in order to get the outputs, output values of each of the signals in the design. This is essentially used in the behavioral simulation step of plan. Now, let me just quickly show how this tool can be run. So here we have provided the command to run this tool. So within the plan directory, we can just basically run this command where we have given the inputs to the Verilog file, the simulation script, the name of the design, and so on. Minus n1000. So this 1000 represents the number of iterations for which we will be running the behavioral simulations. So for the purpose of this demo, I'll just use about 50 iterations. And trial is the name of the output folder where the results would be stored. So once I run the script, you have to just provide a confirmation that we have provided the correct input, since there are a lot of user-defined inputs here. Now plan first performs all this behavioral simulation where the VCD dump files are generated. And followed by that, the processing part takes place, and that's it. So now the results of plan are stored in this directory. The outputs are basically a text file containing the signal-wise side-channel leakage scores of each of the signals in the circuit, as well as some details of the time taken to run and so on. So I can just quickly show how these results look like. So yeah, we just have a list of the name of each signal and the corresponding leakage score, which is basically in the range of 0 to 1. And similarly, the time file, this just basically shows the number of signals in the circuit and the total time taken by plan to run this. So that was a quick demo for a small circuit. We also have many more example circuits and corresponding how to write the simulation script and so on provided in this repo. So now I'll quickly come back to the presentation. So let me briefly discuss how plan, the tool has been validated. So plan has been used to evaluate the Shakti-C RISC-V processor with 430 modules by performing behavioral simulations using the AES-128 as the benchmark. The following figure illustrates the heat map of the results of plan after evaluating the Shakti-C processor design. As we can see, plan is able to identify the most leaking modules depicted in red, such as the register file, D-cache, and so on. Thus, plan can be used for an early estimation of the power side channel vulnerability at the design stage itself. However, plan does have its own limitations. Firstly, plan's statistical approach via the correlation analysis requires a large number of time-consuming simulations to be performed in order to provide a reasonably accurate estimate of the leakage scores. Moreover, plan only accounts for leakage due to the dynamic power consumption, but not due to static power consumption. Lastly, the SVF or side channel vulnerability factor metric used by plan is only able to capture linear correlations between the oracle and the signals in the circuit. Now I'll move on to the second tool, which is Fortify. Like plan, Fortify is also based on the idea that a signal leaks more information if its values have a high correlation with the reference signal. But unlike plan, Fortify applies an analytical approach to quantify this correlation using the notion of signal probability and conditional signal probability. The signal probability is the probability that a signal takes the value of 1 in a design. And the conditional signal probability captures the signal probability conditioned on the reference signal or oracle signal taking a certain value, either 0 or 1. To understand this concept, let us take a look at this visual representation. If the conditional signal probability is close to 1, the value of the conditional signal probability is close to 1, then it means that the signal is highly correlated or highly anti-correlated with the reference signal. But if the signal probability, conditional signal probability value is close to 0, then it means that the signal and the reference signal are not correlated. So from this figure, intuitively, we can understand that if the relative difference between these conditional signal probability values is larger, then there is a higher correlation between the signal and the reference signal, which indicates a higher side channel leakage. So this is the key idea based on which Fortify is developed. Here is an overview of how Fortify works. It takes as input an RTL or gate level netlist design along with a reference signal in this design. And these are operated upon by these 4 modules of Fortify in order to provide the signal-wise leakage scores. Let me take the example of the simple circuit which we had seen earlier and walk through the steps of Fortify. So the first module of Fortify is directed graph representation, wherein it converts the input digital circuit design into a directed graph, where the nodes are the logic gates, the edges are the signals in the circuit, and the edges are labeled with the corresponding logical expressions of the signal. The next step is sub-circuit extraction, wherein Fortify identifies the portions of this directed graph which are influenced by the reference signal. This is done by identifying all the gates and signals which are reachable from this reference signal, which in this case is the gate G3 and the signal out1 depicted in red. And further identifying all the other inputs which feed into these reachable gates. So in this case, it is this input signal Y depicted in blue. The third module in Fortify estimates the signal probability and conditional signal probability values for each signal in the extracted subcircuit. Given these probability values for the inputs of a logic gate, we can determine the corresponding values for the output of the logic gate by applying these incremental signal probability formulae in this table. So these formulae are essentially developed based on probability rules and the truth table of each of these standard logic gates. Now, based on this, Fortify implements a recursive algorithm to find the signal probability and conditional signal probability values for each of the signals in the extracted subcircuit. Finally, the last module of Fortify is leakage evaluation, wherein Fortify applies a novel metric known as the signal probability correlation factor, or SPCF, which is a function of these signal probability and conditional signal probabilities in order to estimate the leakage scores of each of the signals in this extracted subcircuit. So the formula for this signal probability correlation factor we can see from the numerator that it is captures the relative difference between the conditional signal probabilities, which we had seen earlier. Intuitively, it captures the degree of correlation between the signal and the reference signal. And the denominator portion essentially is a weighting factor, which is captures the standard deviation of the set of values taken by the signal. Now, let me give a brief demo of how Fortify can be run. So, in our repository, we have one more README file, which explains all the details of Fortify. Again, Fortify is the main script to run Fortify is a Python script, and internally it invokes a few more Python scripts for each module of Fortify. So the input parameters to Fortify include the name of the input file, Verilog file to be analyzed, some details about the top module in this Verilog file, so that to identify where to start the analysis from, the details of the reference signal, its name and the number of bits in it, and so on. So for comparison with plan, so we'll just consider the same circuit, the 2-bit full adder, which I had considered in the case of plan, and we'll take this command, which can be used to run Fortify. So in our repository, we go to the Fortify directory, and we basically run this command. So as soon as we run this command, immediately Fortify completes the calculation. We can see that it performs the sub-circuit extraction, signal probability calculation, leakage valuation, and so on. And the results are again stored in a similar directory structure. The leaks.txt file stores the list of signal-wise leakage scores. And the time.txt file stores some statistics about the number of signals and the total time taken and so on. Again, in the repository, we have provided some more details for how the input parameters can be provided for a range of more sample input files. And there are also details of how we can compare the results of Fortify with that of plan. So that brings us back to the presentation, where to validate the results of Fortify, essentially we have compared its results with that of plan for a range of input digital circuit designs. And as we can see from this table, the time taken by Fortify is almost 100 times faster than the time taken by plan for each of these digital circuit designs. But at the same time, the high values of the Pearson's and Spearman's correlation between the leakage scores given by Fortify and that of plan indicates the correctness of Fortify. Also, Fortify has been used to evaluate a modern open source SOC design known as the P2P SOC, containing about 3.6 million signals. Fortify takes about 6 hours to analyze this entire design. And for the individual modules in this design, again, the breakup time has been provided. But if we see, compare it with how much time plan is estimated to take for the same evaluation, which runs into several months, this essentially highlights the scalability of Fortify. Let me cover some of the limitations of Fortify. So firstly, Fortify is entirely based on a mathematical model based on signal probabilities. Hence, it does not consider any physical sources of side channel leakage. Also, Fortify assumes that the input digital circuit design is free from reconvergent fanouts, which may not always be the case. So the results of Fortify in such cases may not be as accurate. Also, Fortify assumes that the input design does not have any cyclic dependencies, which again may not always be the case, for example, in case of sequential circuits. To conclude, in this talk, we have presented two open source pre-silicon side channel estimation tools, namely Plan and Fortify. The GitHub repository link has been provided here. The tools are licensed under the BSD 3 class license. Also, we have publications for both the tools. For the Plan tool, it has been published in the Host 2020 conference, and the Fortify tool has been recently presented at the ASP DAC 2022. So we also have a QR code here, which can be scanned to access this GitHub repo containing the details of the code and documentation. Thank you.
Thanks. So there were two questions, but both were answered by your advisor already. So
okay, yeah.
There's one more just coming in. Maybe you can just read the question and answer them directly.
Are the two models validated on silicon? For example, if the design passes the check by the tool, is there really no leakage on silicon anymore? If the design passes the check by the tool, we can say that up to the pre-silicon level, there is not much of a side channel leakage. But again, our tools do not consider the physical sources of side channel leakage. So we cannot really say that there will be no leakage on silicon.
Yeah, possibly just to add to that, we did check a version of the Plan tool which was validated on FPGAs, and although for instance, we had like an implementation of AES which was shown to be less have less leakage than an original one, and we got similar kind of results when DPA or side channel attacks were actually done on FPGAs. We've not yet validated these things on silicon, so this is something which we are actually working on.
Okay. Any other questions from the audience?
Hey, yeah, this is Gang.
Oh, hey, Gang.
Yeah, so I'm just curious for Chester and maybe also Srab. So why this tool is called the Fortify? Is that a acronym for anything, or just no particular meaning?
I don't think we had a expansion for this tool, so I think just called it 45. Nothing much about it.
Okay.
Okay, yeah, because I'm asking because it seems this now becomes a popular word for side channel analysis. There's a company called Fortify IQ that does exactly the same thing.
Oh,
and I know there are some other teams, they are trying to start some big project. It's also called Fortify.
Oh, okay.
Okay. It's a popular name. So
yeah, it's a popular name, yeah.
Yeah. So this is, I think, purely coincidence.
Okay, hey,
okay, thank
Chester,
you.
and hey, thanks, gang. Hey, Chester, Lakshmi, great presentation. We have time for more questions, so we would encourage the attendees to ask questions. I think there is another question coming in. Yeah, go ahead, Lakshmi or Chester, please take that. It's in the QA box.
Yes. So the question is, I'm wondering how the tool can be related to power side channel analysis. It seems that correlation is implemented on the reference and output signals. This is a good question. Actually, the small circuit which Lakshmi had in the presentation, the output signal happened to at least we were looking at correlation with the output signal, but in general, we would actually look at the correlation between the reference signal and every other signal in the design. So for instance, in slide 8, so we've had verify the design or verify the plan to apply the plan tool for an entire processor with around 20,000 signals in the behavioral model, and we would actually get the leakage scores or the correlation for each of those 20,000 signals. So it's not just the with respect to the output, but every signal in the design.
So may I add one thing based on this question, Chester?
Yes, Hank.
Yes. So I was, listening the talk, and I think, somewhere you mentioned about the probability of the signals, and with this, conditional probability, all those things. So it seems, so this is your tool. Does it try to model the cycle accurate execution, or because normally most of the power side channel analysis, they have to go down to, cycle accurate, or even, finer granularities to break, for example, break the keys. And if you're using the signal probabilities, it is not cycle accurate power trace, it is the average power. So I guess that is probably the person, this audience, he or she's asking.
Yes, so this is an excellent question. So most, at least when you look at crypto implementations, most of the inputs have a very uniform probability, right? So when you if your inputs have such a uniform distribution, you can actually use this probability, or what we actually show over here is that this probability would actually work. Now, if you so as long as your inputs have a uniform distribution, the model would be accurate. Now, if you go if you happen to have an input with a non-uniform distribution, then proportionally you would have errors. The errors would actually increase in both plan as well as Fortify as well.
Okay, thanks. So are there any other questions from the audience? So, and also, as I mentioned earlier, we encourage you to explore our CAD for Assurance website to check these tools and trying to download these tools, trying to run these tools yourself. I would say the uniqueness or the main contribution of this CAD for Assurance website is we are not just introducing you the tool, but we are sharing you the tool. Many thanks to all the contributors. Okay.
Hey, yeah, thank you. I have a quick question on Plan and Fortify. How scalable are these tools? You did talk about the runtime, but in terms of different types of crypto, are they applicable to all types of crypto modules?
Yes, Swaroop. So it's not restricted to any specific type of circuit, but any specific type of crypto. We happen to actually evaluated more on the block ciphers, but as such, there's no such restriction.
Did you evaluate on any public key crypto module?
No, we haven't as yet. So we haven't actually tested on public key as yet, but it should very easily be scalable to public key.
I see. That's wonderful. Yeah, great to hear that. Okay. Again, the tool is available for download. So if anybody's interested to try it and use it for his or her own research, please feel free to do that. And that's, of course, the intent of this whole CAD for Assurance initiative. So you're welcome to look at the website and browse the tools, benchmarks, metrics, and make use of those. So looks like there's another question. Can you take that?
Chester or Lakshmy, can you quickly check the question from Jacob?
Have you tested secure designs, as in masked and designs with threshold implementations? Okay, so we have essentially tested masked designs. So what we did do was we incorporated masking at the not in crypto circuits, but at the processor level. It's more details in this paper, in the host paper. So we did see the leakage actually reducing considerably, although it was not actually eliminated. So we do conclude, we were, for instance, able to identify signals which were leaking in spite of the masking.
Not quite sure if the if you can kind of like briefly answer this question, because I from my perspective, we need a long discussion about this. Jacob seems satisfied with that. That's great. So with that said, I think I would like to conclude today's webinar. Sroop, would you like to conclude the whole session and introduce the following the follow-up webinars in April?
Yes, thank you, Ian. First of all, I would like to thank all the sponsors one more time, and also I would like to thank IEEE CEDA. I will thank HSTTC, particularly the support coming from Gang Q and Jane and Sungi Ho. That's outstanding. Really appreciate the continuous support. And I'll also thank Dana Malat from IEEE CEDA, who is helping us with all the logistics and doing an excellent job in that. So again, appreciate it. Then on behind the scene, of course, Amanda Ashbourne from CEDA also has helped. So extend our thanks to her too. We have our next event upcoming in 2 months, and that's on April 22nd. And in that, we will present 2 more tools. These are also available in the CAD for Assurance website. I did put them into the chat box. The first tool is QFlow, quantifying data leakage for RTL IP. That will be presented by Leonard Rayman. The second one is QIF RTL, a new secure hardware description language, will be presented by Xiaolong Guo. We would strongly encourage that you attend. And if you want to attend, you need to register ahead of time. The links to register for these tool demos and webinars are available in the IEEE CEDA website as well as CAD for Assurance website. Okay, and of course, as I mentioned, there are upcoming panels. Panel 4 focusing on secure crypto in pre and post quantum era, opportunities and challenges, and panel 5, hardware assurance versus AI, friend or foe. I think both of them would be really exciting, really informative panels. They're coming up in June and August respectively. So look out for those and register ahead of time. So finally, thanks to all the attendees. Really appreciate your support. Wish you all a happy weekend. Thank you.